Just like the substitution chapter, this chapter we're going to be kind of putting things into an E2 basket and an E2 basket and an E1 basket. So what does the E mean? What does the 2 mean? The other nice thing about this chapter is that a lot of it kind of, if you understand chapter 7, the substitution chapter, well, this should kind of almost be redundant. Like the first question here, what is an E2 reaction? How does the mechanism work? What does the 2 stand for? The 2 in SN2 stood for bimolecular, and still stands for bimolecular here. What does bimolecular mean though? Blank reactants present in the rate determining step. Bimolecular 2, so there are 2 reactants present in the rate determining step. So the remainder of the questions are, well, how does the mechanism work? Is the reaction concerted stepwise? What would the rate equation look like for this? And those are things that I believe you can already solve all by yourself. So take a minute to do this. Pause the video. Go ahead and decide, is this a concerted or a stepwise mechanism? What's our rate? And how does the mechanism look? And then unpause. Okay. So you've done that. And having both reactants present in the rate determining step, we know it's bimolecular, means that this and this are reacting at the same time together. That would mean that it has to be a concerted mechanism, just like an SN2 was a concerted mechanism. What about bimolecularity and the impact of the rate? Well, rate equals the rate constant times the reactants in the rate determining step. Both of those are in the rate determining step because it's bimolecular. So we would just draw the concentration of the alkyl iodide. There we go. And the concentration of the base OH minus. So that would be the rate. What about the mechanism of this? Well, it's a concerted reaction. All bonds are formed and broken at the same time. What are we missing? We're missing this hydrogen here from the product. This base picks up a hydrogen, so it would grab that hydrogen. Those electrons would go down to form the alkene, and that iodide would leave. And all of those electrons would move at the same time. We kind of talked about this a little bit earlier in the packet, but here we're really addressing that this is specific to an E2 mechanism. This is what an E2 mechanism is. This is what an E2 reaction specifics are. And now we're going to move on to what does the reaction coordinate diagram look like for an E2 mechanism. So hold on for a minute. All right, so what would a reaction coordinate diagram look like for an E2 reaction? How many hills would there be? How many a hill is a transition state? 0, 1, 2, or 3. So this would be a good time again to pause the video, fill in your own reaction coordinate diagram, what that would look like, and also try to diagram the transition state structure for the transition state that would be occurring based on our mechanism, and then come back. Good job, you did it. There is only one hill here because as this is concerted, all those things are happening at the same time. We haven't really said if this is exothermic or endothermic, and I would have to look at the actual delta H value, so I'm not entirely sure what we're going to call this. We're going to call this endothermic, and we'll potentially see why later. But so this is what our reaction would look like. One transition state to the product, and this is endothermic because we started at a lower delta H value than we ended, so this is an endothermic reaction. What about our transition state? What do we do there? Again, all bonds that are forming are dotted, all bonds that are breaking are dotted, and then all charges are partial if they are changing. So we would have the carbon iodide bond is breaking, so we'd have a dotted bond to that. Iodide is picking up a full negative charge, so it would have a partial negative charge there. The carbon-hydrogen bond is breaking, so we have that there. The hydrogen-oxygen bond is forming, and we would make that a partial negative on that oxygen. And then what else? There is a carbon-carbon double bond that is also forming, so we would need that double bond there. So that's what that transition state would look like. So these are kind of the specifics of an E2 reaction. Hopefully a lot of them seem straightforward, as they kind of are very similar to what we would see for an SN2 reaction. And the last thing I'll note is what I have written at the bottom of this page of the notes. Note, elimination reactions compete with substitution reactions. But for the sake of learning about elimination reactions, we are discussing just elimination, but we'll move on to discussing both of them shortly. So essentially right now we're talking about just E2. We're going to move on and just talk about E1 later. But then kind of the last thing that this chapter goes into is, well, if SN2 happens in chapter 7 and we're saying similar substrates that E2 is happening now, wouldn't both of them happen? And it turns out that there are some circumstances where only E2 will happen. There are some circumstances where only SN2 will happen. There are some circumstances where both E1 and both E1 and SN1 will happen. So we're going to get into that later in the chapter, but for now we're just discussing elimination as if it's the only thing that's happening. So like I said, we'll get into that soon.